Have you ever found yourself, wrestling with just a mountain of data, trying to connect all these seemingly random pieces of information, and you're just wishing your code could get the meaning behind it all, not just like the raw text? Or maybe think back to when Google suddenly started giving you answers directly, right in that little box instead of just links. That felt like a huge shift, didn't it? It was powered by something really fascinating. And today, we're going deep on that exact technology. Knowledge graphs.
That's right. We're basically going to unpack why these structures popped up, what they really are, how you even build them, and crucially, how they're changing the whole landscape for AI, especially if you're out there building systems. Think of this as maybe your shortcut to getting really fluent in a super powerful concept that's often kind of overlooked.
Okay, let's jump right in. Google's knowledge graph back in 2012. That really changed things, right? It totally shifted what we expected from search. We went from just searching for text strings.
Yeah, just matching characters.
Yeah, just exactly. To understanding actual things, people, places, concepts, and critically, how they're all connected. So suddenly, searching for Taj Mahal, the system knew, okay, do you mean the monument or the musician or the casino? That was big.
It was huge. That knowledge panel that appeared, it became this instant visible proof of concept for literally billions of people. It showed everyone the power of having information that's structured, that's interconnected. It demonstrated what happens when data stops being just, isolated facts sitting in silos and starts becoming this network of understanding. It really set a new bar.
But, okay, that raises a key question, especially for us working with data day to day. Why did we need this connected universe anyway? I mean, relational databases have been the standard for ages, right? They're great for structured tables. So what was missing? What was the limitation?
Well, right. It's not that relational databases are bad. They're just built for a different job, fundamentally. Imagine your data is like a huge city, a traditional relational database. That's like having every single building meticulously cataloged. Perfect rows, perfect columns.
Okay, got it. Very organized.
Super organized. But if you want to find complex connections, say, all buildings by one architect that are also art galleries and within 5 miles of a park, the only way is to constantly build new roads between those catalogs, these join operations, right?
The dreaded join.
Exactly. And as the city gets bigger, your questions get trickier. Those roads become this tangled mess. We sometimes call it a join bomb. It just grinds everything to a halt. Makes finding those deep, multi-step connections super inefficient, maybe even impossible sometimes.
So the core problem wasn't storage. It was meaning.
Precisely. Traditional systems store the data, yes, but not the explicit meaning or the relationships between data points as, like, first-class citizens. They're implied, not explicit. People tried early on, back in the 50s and 60s, with semantic networks. They tried to mimic human memory nodes and edges, but they often lacked formal, machine-readable semantics. The underlying structure of meaning wasn't quite there for machines.
So it was ambiguous, hard for a computer to really process reliably.
Right. That implicit meaning was the big flaw. You couldn't reliably automate reasoning at scale. And that limitation, that need for rigor, led to the development of ontologies in the 80s and 90s. In CS, an ontology is a formal, explicit specification of a shared conceptualization.
Okay, unpack that a bit. Formal, explicit.
Think of it like defining a really precise vocabulary and grammar for your data. Just like a programming language has strict syntax, it brings in the logical structure needed for machines to genuinely reason with knowledge consistently and at scale. It moved from just classifying things to processing meaning.
So we went from intuition, sort of mimicking the brain, to this really logical, machine-friendly rigor, and then kind of combine them.
Exactly. That journey, combining the intuitive network idea with formal logic, is what paved the way for the modern knowledge graph.
That makes sense.
Yeah, and at its core, a knowledge graph really is that blend. The formal schema, the ontology, plus the actual real-world data instances. The equation is simple but powerful. Ontology plus data, knowledge graph. It represents everything as this network. You have nodes, your entities, people, places, concepts, and edges, the relationships, like lives in, works for, is related to. And in one key standard, RDF, it's all broken down into simple triples. Subject, predicate, object, like Paris is capital of France.
Simple, clear. Okay, so beyond Google search, where are these digital brains really making waves in the enterprise? Where are they solving the tough problems?
Oh, the applications are incredibly diverse now. It's really quite impressive. Take finance, for example. KGs are absolutely crucial for fraud detection, anti-money laundering. Traditional databases just drown trying to find complex fraud rings, shell companies, mule accounts.
Right, those connections are hidden deep in the data.
Exactly. But a knowledge graph can surface these multi-hop connections almost instantly. Like, show me accounts sharing a device ID with a known fraudster, and then show me all other accounts linked to those people through shared addresses or phone numbers. JP Morgan Chase uses this heavily for risk management.
It's like getting X-ray vision into those networks,
Yeah.
something tables just couldn't do easily.
Precisely. It's not just faster, you're seeing patterns that were basically invisible before.
Okay, what else?
Pharma and healthcare, massive impact there. They integrate incredibly fragmented data, millions of research papers, genomic data, clinical trial results. This hugely speeds up drug discovery. Researchers can ask really complex questions like, find existing approved drugs that target a protein interacting with a pathway similar to one in this new disease.
Wow, that's specific.
It is. Benevolent AI famously used their graph to flag bersatinib for COVID-19. Mayo Clinic uses KGs, too, integrating patient records and trial data for personalized medicine.
Okay, finance, pharma. What about retail?
E-commerce, yeah. Think hyper-personalized recommendations, much smarter search. It's not just keyword matching anymore. A product knowledge graph connects products with features, reviews, styles, uses. It understands intent. So a query like comfortable running shoes for marathon training, it links shoe type, use case, comfort attributes intelligently.
Right, it understands marathon training implies certain needs.
Exactly. Amazon's Cosmo project even uses LLMs to build common sense KGs for recommendations. They figured out someone buying carnations in May might be buying them for their mother. That's deep understanding.
That's pretty smart.
Okay, one more. Supply chain management, huge area. KGs provide end-to-end visibility that was just impossible before. Instead of these opaque networks, you build a digital twin of the whole chain. Suppliers, parts, plants, routes. Companies like Jaguar Land Rover mapped their supplier network this way. Cut risk by 35%. DHL uses it to optimize logistics, cut packing times by 15%. They spot bottlenecks, predict disruptions.
Okay, these examples are seriously compelling. It's obvious they tackle some really thorny problems by just making hidden connections clear. The potential seems enormous if you're a developer. So if you are that programmer wanting to dive in, what kind of knowledge graph do you build? Are there different types, different architectures?
That's a really important question because, yes, there are basically two main architectural models, each with its own strengths and, ideal use cases. First up is the Resource Description Framework, or RDF. This is the official W3C standard. It's all built on those triples, subject, predicate, object. And a key thing, everything gets a global unique ID, a URI.
Okay, standard, global IDs.
Right. It makes it very schema-driven. You use formal ontologies like OWL, the web ontology language, for really rich semantic descriptions. And you query it with SPAR-ARCUL, which is kind of like SQL, but specifically designed for graph patterns.
So RDF is good for?
It really excels at data integration, semantic reasoning, and interoperability. It's the choice if you need to connect your data to the wider web or build a stable, enterprise-wide semantic layer across lots of different sources. Think of it as building bridges, creating a universal language for your organization's data, great for long-term consistency.
Okay, that's RDF. What's the other main type?
The other big one is the labeled property graph, or LPG. This model often feels a bit more intuitive, especially when you're starting out. Here, both your nodes and your relationships can have labels, basically types, and also flexible properties, just key value pairs attached directly to them.
So more flexibility, maybe? Less strict schema?
Often, yeah. It can be schema flexible or even schema optional. This means you can sometimes get started faster, especially if your data model is still evolving. LPGs really shine for high-performance graph analytics and doing deep traversals following paths through the graph quickly. Perfect for things like real-time fraud detection or recommendation engines where speed and agility within a specific dataset are key.
And querying is different too.
Yeah, query languages are often vendor-specific here. Cypher for Neo4j is probably the most famous. GE School for Tiger Graph is another powerful one.
So RDF for integration and broad semantics, LPG for speed and focused analytics.
That's a great way to summarize it. Your primary goal really dictates the choice. External integration and reasoning points to RDF. Internal high-speed analysis and app building often points to LPG. And honestly, lots of companies are using a hybrid approach now. using both where they make sense.
Sense. You mentioned Neo4j Tigergraph.
Yeah.
Any others people should know?
Sure. Neo4j is a real pioneer in LPGs, known for speed, and Cypher people love its visual ASCII art syntax for patterns. Amazon Neptune is AWS's managed service, handles both RDF and LPG, so it integrates easily if you're on AWS. And Tychograph is built for massive scale, like extreme performance, real-time stuff on huge data sets using their GSQL language.
That's a great overview of the options, but building these, it sounds complex. I mean, these applications are powerful, but getting there must be tough. For our listeners, the programmers thinking about this, what are the real-world pain points, the biggest hurdles in actually deploying a KG?
You're absolutely right to ask that. It's not trivial. Probably the number one hurdle, honestly, is data ingestion and quality. It's the classic garbage in, garbage out problem, but kind of amplified with graphs because relationships depend on clean entities.
Right, if you can't even agree on what John Doe is across systems.
Exactly. Real-world data is messy, inconsistent, siloed. That task of entity resolution matching John Doe to J Doe to Doe John is massive. Plus, just cleaning the data itself. It needs robust ETL pipelines, yes, but more than that, it needs really strong data governance from the start. Rules, processes, ownership.
Okay, data quality is huge. What else?
Scalability and performance. As these graphs get big, billions of nodes, billions of relationships, keeping queries fast is a serious engineering challenge. You often have to move beyond just vertical scaling, buying a bigger server to horizontal scaling.
Spreading the load across many machines.
Right, using techniques like sharding, which works, but definitely adds complexity to your architecture and management.
I guess they're never really finished, are they?
That's a third big one. Maintenance and evolution. Knowledge changes constantly. New data comes in, your understanding of the domain deepens. Your graph schema, the ontology, needs to be flexible enough to adapt without breaking everything you've already built. This is where newer tools, sometimes even using LLMs, are starting to help automate schema updates, but it's still a major ongoing effort.
So building a knowledge graph, it sounds less like just a tech project and more like a real test of an organization's whole data discipline.
Right.
It forces you to get your house in order.
That's a perfect way to put it. It really does. Which actually brings us neatly to the really exciting recent development, the powerful synergy between knowledge graphs and large language models, LLMs. This is where things get really interesting now.
Okay, the LLM connection. We hear so much about them, but also about the problems, right? The hallucinations, the stale knowledge, the fact you can't easily tell why it said something, the black box problem. How does a knowledge graph actually help with those specific issues?
It's like they were made for each other, addressing each other's weaknesses. LLMs are amazing at language, but yes, they hallucinate facts, they lack built-in explainability, their knowledge gets outdated, they often lack deep domain context. A knowledge graph acts as this external, verifiable source of truth for the LLM.
Grounding it in fact.
Precisely. It grounds the LLM's responses in the structured, factual data within the graph, which drastically cuts down on hallucination. And because the graph is explicit, you can literally see the nodes and edges connecting the facts. It provides the why. It gives you explainability.
So a glass box for the LLM's black box.
Exactly. It fosters trust. Plus, you can update the KG in real time, feeding the LLM current dynamic information, solving that staleness problem.
Okay, so the KG helps the LLM be more accurate, explainable, and up-to-date. Does it work the other way too? Do LLMs help KGs?
Absolutely. It's definitely a two-way street. LLMs are becoming incredibly powerful tools for building knowledge graphs. Think about extracting all those facts and relationships automatically from mountains of unstructured text PDFs, reports, articles. That used to be a hugely manual, slow process.
The bottleneck you mentioned earlier.
Right. LLMs are now automating a lot of that extraction, making KG creation much faster and more scalable.
That makes total sense. And I know there's this cutting-edge technique tying these together called graph RAG. Can you break that down for us? How's it different from normal RAG?
Yeah, graph RAG is really cool. So standard RAG retrieval augmented generation usually works by finding chunks of text that seem similar to your query, right? It pulls those text snippets and feeds them to the LLM as context.
Okay.
But that approach struggles with complex questions that require connecting information from multiple places, what we call multi-hop questions. It just gets isolated text bits, missing the links between them.
Like getting puzzle pieces, but no picture on the box.
Good analogy, exactly. Graph RAG is different. It uses the knowledge graph itself as the retrieval source. So instead of just finding a relevant text chunk, It first finds a relevant starting node or nodes in the graph, maybe using keyword or vector search. And then critically, it traverses the relationships in the graph outward from those starting points. It gathers this interconnected subgraph of relevant entities and relationships.
Okay, so it pulls a whole connected network of information, not just isolated facts.
Precisely. Let's take a complex example. Which drugs treating diseases linked to the BRCA1 gene might interact badly with drugs for elderly patients with heart disease?
Whoa, okay, that's multi-hop for sure.
Definitely. Standard RAG would struggle to piece that together from separate documents. GraphRag would start at the BRCA1 node, follow links to associated diseases, then to drugs that treat them. Simultaneously, it finds nodes for elderly patients and heart disease, finds their common medications. Then it looks for interacts with links between those two sets of drugs. It gathers that whole structured subgraph and feeds that to the LLM. The context is far richer, far more connected.
And the answer is traceable back through the graph path, explainable.
Exactly. More accurate and fully explainable. This whole convergence means KGs are really becoming the foundational semantic layer for enterprise AI. The central map describing the whole data ecosystem. They're becoming multimodal, integrating images, sensor data, everything. They are truly the verifiable, auditable backbone for AI that's intelligent but also trustworthy and explainable. The digital brain, as you said.
Wow. Okay, so thinking about that, for you, the curious programmer listening, with this vision of knowledge graphs as the enterprise digital brain, providing structure, context, memory for AI, how will you use this power? How will you build apps that aren't just smart, but are genuinely intelligent, trustworthy, and truly explainable? Something to think about. Well, that was an absolutely fantastic deep dive. Really eye-opening. It's so clear that knowledge graphs are way more than just a fancy database. They're actively shaping how we interact with information and build the next generation of intelligent systems. If this sparks your curiosity, definitely keep exploring. There's so much more out there.
Absolutely. The whole story of knowledge graphs is really about our ongoing quest to organize and understand the world. Now we just have machines as incredibly powerful partners in that quest. Keep asking those big questions. Keep connecting those dots.
Until next time, keep learning, keep building, and keep making those incredible connections.